Hello everyone, welcome back to my YouTube channel. I am Priya.S of 3rd SEM pursuing my Information Science course in Sri Venkateshwara College of Engineering. Today I am going to discuss a few topics in the subject Data Structure and Applications. The subject code is BCS 304. The topic is Dynamic hashing, leftist trees. Dynamic hashing and leftist trees. Overview of the topic. Data structures are foundational in computer science, affecting performance and efficiency in various applications. Focus areas. Explore dynamic hashing and leftist trees, their properties, operations, and applications in real-world scenario. Dynamic hashing definition. Dynamic hashing is a strategy for creating a hash table that dynamically adjusts its size based on the number of elements, ensuring efficient access and minimal collisions. Motivation. Traditional static hashing can lead to inefficient memory usage and performance degradation when the dataset changes. Key concepts of dynamic hashing. Buckets structure. Each bucket can be a linked list or an array that holds multiple entries. This prevents loss of data when multiple keys hash to the same index. Splitting. When a bucket exceeds its capacity, it splits. The keys are rehashed and redistributed into new buckets. Directory. Mapping acts as a table of pointers to the buckets. As the number of entries grows, the directory itself may need resizing. Resizing. When resizing, the entire hash table might need to be rebuilt, but this is done infrequently. Load factor. Definition of load factor. Load factor is equals to number of entries per number of buckets. Threshold. A typical threshold is 0.7. If exceeding this value triggers a split and resizing operation. Performance of dynamic hashing. Average time complexity. Insertion O of 1 on average due to direct access via hash functions. Deletion O of 1 on average, especially when managing linked lists within buckets. Lookup O of 1 on average, enabling fast data retrieval. Worst case degradation. The worst case scenario occurs during high collision scenarios leading to O of n if many entries hash to the same bucket. Mitigation. Use of a good hash functions minimizes the chance of collisions and maintains performance. Applications of dynamic hashing. Database systems used in indexing to speed up queries. For example, when searching for user data, dynamic hashing allows quick access based on user IDs. Memory management. Dynamic allocation strategies in operating systems utilize dynamic hashing to manage free memory blocks efficiently. Caching mechanisms. In web servers, caching frequently accessed data like user sessions can use dynamic hashing to keep performance optimal as access patterns change. Leftist trees. The definition of the leftist trees: a self adjusting binary tree used primarily for implementing priority queues where nodes can be merged efficiently. Characteristics: balances itself during operations to ensure that the left child always has a higher rank than the right child. Key concepts of leftist trees. Heap property. Each parent's node's value is less than or equal to its children values, making it a mini heap. Leftist property ensures that for any node, the left subtree's rank is greater than or equal to that of the right subtrees. This helps maintain a relatively balanced structure. Rank. The rank is the shortest distance from a node to a leaf. This ensures that the leftist tree remains efficient in merging operations. Operations on leftist trees. There are many operations in leftist trees like insertion, complexity, merging. Insertion. Create a new node and merge it with the existing tree. The merge operation will maintain the heap and leftist properties. Complexity O of log n. Deletion. Extract, mine. Remove the minimum element root and merge its left and right trees. This operation ensures the tree remains a valid leftist tree. Complexity O of log n. Merging. Merging two leftist trees is efficient and is a key advantage. The smaller tree is merged into the larger one, adjusting ranks as necessary. Complexity of log n. Applications of leftist trees. Task scheduling. Systems that prioritize tasks like CPU scheduling can use leftist trees to quickly retrieve the next task based on priority. Event driven simulations. Useful in simulations. Example: network simulations where events are processed based on their scheduled time or priority. Implementing other data structures. Leftist trees can be used to create more complex structures like Fibonacci heaps, which offer even better amortized time complexities for certain operations. Applications of leftist trees. Task scheduling. Systems that prioritize tasks like CPU scheduling can use leftist trees to quickly retrieve the next task based on priority. Event driven simulations. Useful in simulations. Example: network simulations where events are processed based on their scheduled time or priority. Implementing other data structures. Leftist trees can be used to create more complex structures like Fibonacci heaps, which offer